Start. Good afternoon, everyone. I would like to welcome you to the next QSimFP webinar. And today our speaker is Tobi Haas from the Université Libre in Brussels, in Belgium. Tobi is going to discuss quantum features from classical entropies, which is work done, I believe, in Heidelberg. So, Tobi, without any further delays, please, the floor is yours.
Thanks a lot, Patrick. It's a pleasure to be here today, even on a public holiday. So in Belgium, we're actually celebrating the end of the First World War today. But nevertheless, I'm very happy to join this rather cool consortium and talk about how we can understand information in space-time in a way that it's actually accessible, especially from an experimental perspective. As Patrick said, this is work done together with two groups. One of them is in Heidelberg, which is, of course, the one by Markus Oberthaler. And the other one is by Martin Gärtner, became professor 1.5 years ago in Jena, interested in quantum optics, quantum information, stuff like that. And if you find any of what I'm saying today at least partially interesting, you are invited to read one of these publications. The first one is a rather theoretical one. It's my first solo author paper, and the other two are together with the other guys, more focused on how it can actually be done in an experiment. Okay, I just had a look at the QSimFP website and tried to gauge a bit where we should start. And I thought it might be good if we really start at zero and first of all define precisely what information is and what entropy from an information theoretic perspective actually measures. So let's start from a classical perspective. For instance, consider something like a single coin. And instead of just having heads and tails, let's say the two sides are blue and red. Then the possible event is something like a mixture of the probability of landing blue plus the probability of landing red, both weighted by blue and red, whatever this should be, now that these are words and not numbers. And the question is now, given some classical probability distribution, how much do I know about the coin and the possible events that will happen? In order to answer this question quantitatively, Shannon introduced the entropy named after him, the Shannon entropy. You can see the formula on the right. And we will go through why he defined the entropy, which should measure the missing information about this coin given the underlying probability distribution, and why he defined it that way. First of all, we would say that we miss information about something if the probability of observing it is rather low, which means a good measure of missing information should somehow be inversely proportional to the probability of an event. Given that the entropy formula has a logarithm, this is why we have something like minus ln of pi. Second, we want that the information of independent events or systems add up. Why? If there are no correlations between two tosses of a coin, the missing information should simply add up. And it is rather easy then to guess, okay, we need something which under the usual product rule of independent probabilities turn into a sum. And well, this is because we have something like the logarithm in the entropy formula. And last but not least, we would like to do this for all possible events, which is why we have something like an expectation value with respect to the probability distribution of interest. This ensures that the whole functional is non-negative. Sounds good. We shouldn't be able to know more than everything if entropy measures missing information. And also it should be zero, meaning we know everything about the coin precisely if and only if the outcome is known. So in case P is 1 for one event and 0 for all others. For this particular example, calling P1 P, then P2 is 1 minus P. The entropy as a function of the probability looks like this. In both cases where we know it's either red or blue at 0 and 1, entropy is 0, and it's maximal in between. The missing information about a coin is maximal when it's really random, when P is exactly 1/2. So I hope this convinced you that this definition of the entropy has some intuitively acceptable properties. And since we are interested in quantum features, let's see how this extends to quantum systems. For quantum information, the archetypal system is something like a single qubit where red and blue are now exchanged by the pure states 1 and 0. And instead of having some mixture with respect to the probability, we now have the notion of mixed states, which of course can be written as some mixture of pure states. In this case, the uncertainty in the underlying probability distribution, the missing information, so to say, lies in how mixed the state is. How precisely do I know the state? And therefore, the quantum entropy measures something like the mixedness. It's still a measure for missing information, but just for intuitive reasons, I would say it measures mixedness. Let's see how this all transfers. It should increase with the state's mixedness. You have seen here the sum has been replaced by a trace. The probabilities have been replaced by the density operator, but still the property that it's somehow inversely proportional to the density operator holds. The same holds true for information of independent systems. If we have a tensor product, we get a sum for the entropies as it should be. Further, it's still a non-negative quantity, being 0 if and only if we know the state, i.e., if the state is pure. So for a qubit, this curve actually looks precisely the same if we assume the state to be diagonal in this 0-1 basis, and if we call P the probability that you land up or down. So in this sense, the quantum entropy is a straightforward generalization of the classical one, but of course relies on the density operator, so measures the quantum information. Now, in which sense is quantum information different to classical information? Or in other words, do quantum entropies have other properties than classical entropies? The simple answer is yes, and you can see these differences when you study entanglement, or generally the correlations between two or more systems. Therefore, let's consider now two qubits labeled by A and B. We associate to them a global state ρ, global in the sense of for the bipartition, and local states obtained by tracing over the complement. The question is now, what does entropy tell us about the correlations between A and B and potentially about the entanglement between A and B? In a classical theory, and with classical I mean that we only can have classical correlations, meaning that we have separable states, for instance, a product state or a mixture of product states, but certainly nothing entangled, we find the following behavior of the quantum entropy. We find that, and this is, to be honest, the way more intuitive thing, that the missing information about the global system is always larger than the missing information about the parts. This means, in particular, in the special case where the global state is pure, so when S of rho is 0, this strictly implies that also the parts have to be in a pure state. In simple words, in classical theories, if we know the full system, we therefore know all about its parts, because global entropy implies, global entropy 0 implies local entropy 0. However, we know that in quantum theories, there is the possibility of entanglement. And this has some rather interesting implications, namely for a general state ρ, so some state that is not of separable form, it is possible that this inequality above is reversed. Meaning it is possible, and this is the extreme case, that S of rho is 0, so you know still everything about the total system, and at the same time, you know something, you do not know everything about the parts because S of rho A and S of rho B are positive. So quantum entanglement can mean, this is not true for all entangled states, but it's a very good intuitive reasoning, that it's possible to know the system and knowing nothing about its parts. So in order to look for entanglement, it's always a first good guess to look at, well, if the full system is pure and the local systems are not, then it can only be entanglement. Okay, so this is what entropy is doing in the sense of witnessing entanglement and describing in information theoretic terms what's happening. So now let's get into the main topic of this talk, namely how can we assess information in space-time? And with space-time, I really mean anything from a spatial region at a fixed time, or also something which is simply a Cauchy hypersurface. It could be a black hole. It could be a set of modes in a BC experiment. In all cases, we would like to understand how does the information depend on how big my spatial region is, or does it depend on its geometry and all these kind of things. So how is information encoded in space-time? Now, the general setup for this question is as follows. We ask for the entanglement. So usually we consider a globally pure state to make our life easy in a subregion. In a continuum, so when you have something like a quantum field, then the easiest setup is a one-dimensional real line, and you pick out some finite interval A of length L and ask how much is it entangled with its complement given a set of typical states, such as ground state of a theory, a state obtained after a quench, something like that. And in the mode picture, so something which is happening in an actual experiment where you have finite resolution, you can think of this as having many modes. And for the rest of the talk, we will focus on bosons, but you can also make similar conclusions for fermions and spins. Then you expect something like a very particular form of how the information is encoded in space-time if the coupling between neighboring modes is local, depicted here by these triangular shapes. And this is, of course, something you always have in a quantum field theory, or usually quantum fields are local in the sense that you have a derivative term, the kinetic term basically, whereas in lattice models, you often have next to nearest neighbors. So if interactions are local, or couplings are local, then you expect the following. Namely, you expect that the information of the subsystem A scales like the area of its boundary, something the cosmologists may know from Wittgenstein's formula for a black hole. This is, of course, very related, and people are thinking extremely hard how exactly it is related. And for quantum field or the many-body system, this is usually expected for ground or quench states of gap theories or simply low-lying states. Whereas if the subsystem would be in a thermal state, and we know the thermal entropy should be extensive, we would rather expect something like a volume law. Similarly, the mutual information, which is a measure for the total correlations between A and B, and with total, I mean it is zero if and only if there are no correlations at all, at whatever order, or it's positive when there are correlations. For the same setting, you find rather strong correlations when you have area law-like scaling for the entropy, and rather weak correlations when you have thermal states. These are very general findings. I could cite I don't know how many people who worked on this. And the question for all of these is, Okay, well, this is nice, but all depends basically on knowing the local state. In the continuum, this is for free theories doable. For lattice models, it is also computable to a certain extent, but experimentally, in the many-body regime, this is very hard. If you don't have too many modes, you can try to perform state tomography, provided that the individual modes are spins or something with low-dimensional Hilbert spaces. There have been extremely clever people trying to design readout techniques which give you directly the entropy and not just the density operator, for instance, using randomized measurements or copying the system. But they are really either restricted to spins again or to just a handful of modes. Or instead of trying to measure the mutual information, people have been interested in measuring higher order correlation functions and trying to learn something about the full set of correlations from there. But of course, all of them would be most interested in full measures of information and correlations, but it's simply hard to get them. And this was the motivation for us to go one step back and ask a somewhat provocative question, namely, do we actually need quantum entropies? Do we actually need the local state in order to probe these phenomena like area laws, transition to volume laws, in general, to probe how information is encoded in spacetime? I know that this is somehow different to what most people in the field try to do. They simply try to come up with even more clever readout techniques, and many of them are actually super great. But we simply wanted to ask a more fundamental question in a sense, and the answer is in the affirmative. So we will talk about what I mean by saying classical entropies and how we can get out quantum features. We will look at the scalar field as an example from the theoretical perspective. And then, of course, since I advertised so much that at the end of the day we would like to use it to measure something, we talk about the experimental perspective, more precisely a spin or Bose-Einstein condensate, where in simulations we have seen that using these methods, one can indeed observe area laws, volume laws, thermalization, all these kind of things by just looking at the data and not imposing anything else. Okay, so classical entropies. We have seen the definition before. The question is now, how can I use this now in an experiment or given some experimental data? Well, first of all, we have to define, especially in the continuum, what we are actually measuring. In a bosonic theory, we are usually interested in some field operator phi of x with conjugate momentum field operator pi of x, conjugate in the sense that the two fulfill canonical commutation relations, but just with a Dirac delta instead of a Kronecker delta in the continuum. Therefore, the set of fundamental fields for a large class of theories are a scalar field and its conjugate momentum field. And what I mean here are the classical fields, so not bold symbol, normal symbol phi and pi, and you can get them in the same way you would in quantum mechanics, where phi is simply position x and pi is simply position p, namely by working in the Schrödinger picture and saying these are the eigenfields instead of eigenvalues of the corresponding field operator. Just to make this very clear, it is really nothing but the multimode generalization of having a single harmonic oscillator, in which case the field phi, the classical field, is the position, and an experiment would simply repeatedly measure many, many of these positions, and from there get something like f of x, so overlap squared, wave function squared in the case of a pure state. And this is all we want to look at. So at the classical distributions corresponding to measuring x, which in the field theory case is an infinite dimensional distribution over field configurations. To make this even clearer, let's take the picture from before. and look at the discretized case where both phi and pi at every discrete position j would take many different possible values, some more probable than others, depicted by strong lines compared to rather thin lines. And the field theoretic generalization of this f of x, which I call O of nu, is nothing but the functional probability density for every possible classical field configurations. Just as in this case, we have the classical probability density for each position x. Of course, in the quantum many-body experiment, this would simply be a high-dimensional but finite-dimensional probability distribution, and that's it. Now, there are three, I would say, common choices, or let's say, from my perspective, standard choices for which measurement distributions to pick. Let's say we are in phase space, so have both phi and pi. Then from a theoretical perspective, what would be interesting is the Wigner distribution. It somehow, not necessarily in a clear way, encodes the information of the full state, but can be negative at times. So therefore, it's really hard to get experimentally, especially in the many-body regime, but is of quite some importance for simulation because of the truncated Wigner approach. So let's include it in the discussion. More suitable for experiments are the so-called marginals, so the field theoretic generalization of this f of x, and of course the same for g of x, or now g of pi. And they call them marginals because you can get them from the Wigner by marginalization. The third distribution, less known outside of quantum optics, but becoming more and more relevant for many-body experiments, is the Husimi distribution. And it's something like the Wigner distribution convolved with the vacuum. It is the optimal measurement of having phi and pi at the same time, but since they don't commute, you have to pay a price in terms of some additional noise, which is why it's always wider than the Wigner distribution. So we consider these three, the first for theoretical interest, the second for experimental matters. And instead of trying to get the local state, we look at the local distributions. So by simply integrating out degrees of freedom outside of this interval A. Now, if we have these measurement distributions, and this is what experiments produce all the time, they basically sample from them. The question is, what information can we extract from that? Now, the first thing would be to say, okay, we simply associate the classical entropy as before. Please don't worry, we just have generalized the notion of entropy a bit according to a guy called Reni. And he introduced this parameter R, which is positive, real, and unequal to 1. You can only take the limit R to 1 using Hopital's rule, in which case you get back the normal entropy. It's just a generalization, which from an information theoretic perspective is always something you would like to have. So if you just apply now this definition, it's the same as before, now just for this functional over field configurations. What would we get? What is the missing information in the measurement distributions? Well, in the case where O is a distribution over both phi and pi, so a W or Q, we should actually take into account that distributions in phase space are constrained by the uncertainty principle. And there is a big community in quantum information concerned with entropic uncertainty relations, which are stronger versions than the usual second moment-based ones, which tell you you cannot know at the same time position and momentum distributions arbitrarily well. This is just the uncertainty principle, and it's of course very natural to try to express it with informational quantities. And it simply tells us that these entropies are lower bounded, so have a minimum value of missing information, when the distribution corresponds to the vacuum state, here denoted by a bar. And I really have to clarify here what I mean by vacuum. And please think in terms of the mode picture, in which case vacuum means every single individual mode is in its vacuum state, for which, interestingly, the entropy is finite, not zero. And we take a tensor product over all, so independent vacua. Now, we just learned from before, if you have an entropy over independent states or distributions, the entropy is extensive. And therefore, if this entropic uncertainty relation holds, and it does, we know that the classical entropy is always lower bounded by something like a volume law. Now, this sounds like bad news. We have just defined the normal entropy of the measurement distribution, and we always get a volume law independent of the state we look at. And the admittedly super stupid idea we had was by saying, okay, well, if there's this leading order volume law, let's see what happens if we just subtract it and consider the difference between the left and right side of this entropic uncertainty relation. So look at the next two leading order terms. And surprisingly, this quantity, which I denote by delta S, you can already see immediately that this is related to something like entanglement. Why? Because the very same argument I gave to you before for the quantum entropy, namely that if the local information is greater than the global information, this is a sign for entanglement. The very same thing holds for this classical thing as well. So you can easily prove that if rho is separable and if O is a distribution over both phi and pi, remember you always need non-commuting observables to learn something about entanglement, just as in the Bell test. Then the so-called conditional entropy, which is nothing but global minus local, is bounded from below by 0. And for some entangled states, this is violated. So in this sense, this quantity behaves exactly as a quantum entropy. And therefore, we should have a closer look at its properties in the many-body regime. At the same time, we would like to understand what the classical, again generalized, so therefore Reni, mutual information tells us about the correlations in the system. There we don't have to subtract anything for the simple reason that it's already some type of relative quantity. If you look at the three terms in there, if you subtract from the first SR of rho A bar, the same for the second, but then at the end you have minus the total entropy, and knowing that for O bar, everything is additive because it's a product state, it simply cancels out. So therefore, the classical Reni mutual information, in a sense, is already a subtracted quantity and should therefore tell us something about correlations, just from the perspective of the measurement distribution. So let's check these out. Let's see what happens if we compute these for a few standard cases. We start with the scalar field. So for theorists, this is of course the prime model of quantum field theory. You simply have the Hamiltonian, and I apologize for those who prefer the action, which actually includes myself. The Hamiltonian operator, which starts with the momentum field operator squared. Then you have this local term I was mentioning before, the kinetic term, something which tells you that interactions are local and of course leads to expectations that information should also be local, and some mass term. Now, in order to compute the entropies, what do we have to do? Okay, first we have to pick a set of states which we believe have interesting information entropy properties. Then we have to compute the measurement distributions, plug them into the formula, and look at what comes out. I find it very instructive to give you the general form of typical local measurement distributions. What I mean by typical is low-lying distribution, something close to the ground state. Now, since this is a free field, the ground state is of Gaussian form. I know that some people prefer to refer to this as the linear theory, and therefore the ground state is of Gaussian form, meaning that we are now in the continuum, we don't have sums in the exponential, we have now integrals over all spatial positions, and this is actually a well-defined operator, this whole integral thing. And in there, the covariance matrix, more precisely its inverse, is nothing but the two-point correlation functions of phi and pi with respect to the distribution we are looking at. In case this is the Wigner distribution, these are the true two-point functions, so the ones we are always calculating. But there's also something else. I mean, if we go beyond the ground state, so for example, look at a single particle flying around, then we would also have something like a polynomial in there. And please keep in mind the connection to ordinary quantum mechanics. The first excited state of a harmonic oscillator is just the Gaussian for the ground state times something. This is the distribution, so therefore quadratic in X. And in general, you have Hermite polynomials in there. And for the field theory, it's very similar. It's simply that the polynomials get a bit more complicated, but it's still some type of Hermite polynomials in the case of O being F and G. So in general, you have something Gaussian times a polynomial in the fields. Okay, this is already something. It's a rather general ansatz, I would say, but still we can compute a lot. What do we find? Well, there's a lot of calculations to be done in between, and I hope you believe me. It took me quite some time, to be honest, and was a bit stressful at times to play with all these non-Gaussian things and so on. Entropies of non-Gaussian distributions are always a bit more tricky to calculate, but at the end we managed. And the Gaussian and polynomial parts decompose linearly in the final formula for the entropy. Now, for those of you who know how entropies for continuous distributions look like, the first term in here is just the ordinary entropy of a Gaussian distribution up to an E in the determinant, which is missing here because the Wigner distribution is differently normalized. And look at that, what we have there, the second term. This is the volume law I've been talking about. We have argued it comes from entropic uncertainty, but now we see it actually also comes out from the calculation. It's independent of the state and just has this L over epsilon. And please don't worry, this 1 or 2 simply means if I have a marginal distribution, in which case I have only one relative dimension, so 1, or if I have a phase-based distribution, in which case we have the 2. Now the non-Gaussian part is substantially more involved, and please, I skip the details. I hope that's okay for you, but to give a rough idea, it's similar to computing Feynman diagrams. It's not exactly the same, but similar in the sense that you perform the derivative trick, so bring all the polynomials outside of the integral you have when writing down the Rényi entropy, and then compute everything by taking derivatives at 0. So it translates into a combinatorial problem, but the directions in these graphs actually matter, and therefore it's not exactly the same as Feynman diagrams, but it can be solved diagrammatically. So the important part is now we said we don't want the classical entropy, we actually want the subtracted one. Now what happens if we subtract the vacuum? Well, the vacuum is Gaussian, so we don't have this non-Gaussian distribution. The volume law we have for all states, so when we subtract the entropy of 2 of them, it simply goes away. And in this first part, the 2 pi cancels, and we have the inverse of the vacuum covariance matrix. This is the general formula for the subtracted classical entropy for a typical state. And similarly, we find for the Rényi mutual information very, very similar terms, but now simply everything relative to each other because the mutual information is a relative quantity. Okay, I have claimed that these quantities should somehow encode the things of their quantum analogs. So let's look at examples. Let's see if this is actually true. Area laws. Let's start with the class of Gaussian states. This encompasses the ground state, but also thermal states, for instance, of a free theory, a linear theory. For Gaussian states, one can actually find a very strong relation indicating that the two can actually be identified, namely the Rényi 2 entanglement entropy, so the entropy of the local state rho A, is actually equal to the subtracted entropy of the Wigner distribution for arbitrary R. think this is also interesting that on one side we have a fixed R, namely 2, but on the other side we don't have a fixed R. Further, if the Wigner distribution is a product over field and momentum field, which is the case for both states I mentioned before, this further decomposes into the sum of the two marginal entropies, showing that in the case of the ground state, which is the archetypal example for area laws, we expect that the ground state classical subtracted entropies behave exactly like quantum ones. And this is also what one finds. So the continuous curves are analytic calculations with the formulas from before. The points are simply additional numerics on the lattice to see that everything matches. And the 4 colors are associated to the 4 different distributions. And we see that all of them follow the important logarithmic scaling. In one dimensions, the area law is the logarithm of subsystem length over some cutoff epsilon, for instance, the lattice spacing. And more importantly, the central charge C, which in the case of a scalar field is 1, appears in the scaling. So for the Wigner distribution, we find C over 4. For F and G, we find C over 8. And for the Husimi, I'm actually not so sure whether C has to appear there or not. So I will not make any strong claims what happens in there. But still, you find an area law for the Husimi distribution. Another class of theories are if you have a thermal state, but not necessarily a local theory. What am I talking? If you have a thermal state of a local theory, but not necessarily the theory I have shown to you before. So for any thermal state of any local theory, which is necessarily of this form, we find area laws in the mutual information. So these are like the curves I've shown you before, and you can strictly prove, and this is what I've done in the first paper, that the mutual information for these class of theories and states is bounded from above by some constant times the area of the surface separating the two regions. Also, I have said it would be interesting to learn something about non-Gaussian states, like particles, for instance. And if you consider particles with high energy, and high energy because low energy means that the local states look very similar. So we want to look at something where the information is expected to change. We find the following behavior. We find that the additional entropy, remember, the full entropy of a non-Gaussian state is ground state plus the other contribution. And this plus other is depicted by the small delta. Looks like this. In all cases, we have something like a logarithm of some polynomial in system size over total system size. And therefore, we can always bound this by an area law type curve. But what I found super interesting is the black curve. It's for the Wigner distribution. And if you remember from before, the plot I've shown to you for the coin, this looks actually very similar. And it's not only similar, it's actually the same. So the additional entanglement of a single particle in the quantum field is like a coin in the sense that the probability of flipping heads in this case is the probability of the particle being in the subinterval you have chosen. So in this case, the probability is simply subsystem size over total system size. And given that the particle has high energy, this actually makes sense because in this case, it's equally distributed over the whole system. And it just matters how big the subsystem is with respect to the total system. So from a theory perspective, I was satisfied when seeing all of this. This is strong evidence that the classical entropies display the very same properties as the quantum analogs. But to test the initial promise, which was this could be useful for experiments, we should also look at that. Motivated by the capabilities of the Markus Oberthalers group in Heidelberg, we looked at a spin 1 Bose-Einstein condensate. And I really have to say, and please don't get me wrong now, for me, a strong motivation for looking at such a system was that it's simply super complicated. There are lots of different dynamics happening, and if we can show that for such an involved system, we can actually say something given experimental constraints, that then this is a rather strong argument for why the method we propose should work. So what is happening in this experiment? They start from a coherent product state and then perform a quench. The quench dynamics has the following components. Spin 1 means the individual atoms have a spin component, and in the external magnetic field, this splits up into magnetic hyperfine states, denoted by MF. And for the F equal to 1 manifold, we have -1, 0, and 1 for MF. Now, we have in there the quadratic Zeeman shift, denoted by Q, which simply shifts the energy of -1 and 1 above the energy of 0. We have all atoms independent of their hyperfine state colliding all the time, which is controlled by this C0 and the density-density interaction. And this is, of course, responsible for spatial movement in there. And then additionally, they can shine in radio frequency fields, which effectively take two atoms in the MF equal to 0 manifold and pump them to the +1 and -1 manifolds. Of course, we need momentum conservation for that, so we always have +1, -1 pairs. So also in the spin degree of freedom, there is something happening. And now, because we want everything, like we want to have well-defined notions of local subsystems, we have chosen to say we have a lattice of this 20 times small BCs, and all of them separated by some well potentials, giving an effective interaction between neighboring wells controlled by J. So a lot of stuff happening. And in the readout, we are considering spin observables, spin operators, which effectively correspond to the fields we have considered before, this phi j and this pi j. For completeness, this is how they are defined. So spin operators with respect to the spin degree of freedom. And the only remaining task is now the experiment, of course, produces data in the form of destruction. So every single time they simply measure, in this case, the Husimi distribution. So it's a joint measurement of phi and pi, a single sample of these two observables, phi and pi. And if they repeat it, they get something like a sample distribution from the underlying Husimi distribution. And the question is now, can we get the entropy from that? And the super cool answer is yes. And you don't even need to know the probability distribution itself, because there is a very simple algorithm called the KNN algorithm. And maybe algorithm is too much to say because it's implemented in 2 lines of code. And the idea is to say a good estimator of the entropy is some function. I will not go into details here. It's analytic, but more importantly, has somehow an idea of how close the samples are, because this tells you something about whether they are in a region of high density or not, in which case they would be close or not. So this ln of epsilon in there, this epsilon is nothing but the distance of the kth sample to its, the ith sample to its kth neighbor. So all you have to do is choose the k, which tells you choose the kth nearest neighbor, and then you sum over all these distances. As said, easy to implement, and from a mathematical side, it's a very nice choice because it's asymptotically unbiased, so it's a true estimator. We estimate the entropy directly from the data and therefore make no assumptions on the underlying state. In particular, we can use it if the state is non-Gaussian, which is what is happening in this experiment at late times. Okay, so let's look at the experiment. Again, this was simulation, truncated Wigner. The data points are what we got from the simulation. We also have a Gaussian analytic model for early times. And all continuous curves you see are area law fits. So we fit the functional form we expect. Initially, everything in product state, all measures of information and correlations are zero. And then correlations are slowly building up. And more precisely, they build up in exactly the way we expect, namely in this logarithmic form. To convince you that it's really logarithmic, please look at the dashed line here, which would be the linear fit to the first two data points. So it's definitely sublinear, but actually the fit, I would say, fits rather well the data points. So we can observe the dynamic buildup of quantum correlations and the appearance of an area law because couplings are local. At later times, remember this is a quench experiment and we are looking at a subsystem of the 20 wells. We would expect something like local thermalization, and this is exactly what we see in the entropy curves. Initially, the green is the same in both of the two rows. We go from a logarithmic type of behavior to a linear behavior, in particular to something stationary. At the same time, correlations are going down again, which is exactly what indicates local thermalization. So we see first area laws, we see then the volume laws, and therefore conclude that we have observed local thermalization through quantum correlations. On top of that, the incline of these curves give you the local temperature. More precisely, its inverse, free. Let's look at videos. I hope you saw the wiggling here at the end. This is also something I always mention because at the very end, the distributions are rather non-Gaussian. Entropy estimation becomes harder in this regime. And therefore, you see that this, remember, this was a fit, the curve. The points themselves do not wiggle as much, but simply shows you that, of course, the method has limitations precisely when the underlying distribution becomes super weird. Okay, let's wrap up. I think I'm already over time. On the theoretical side, we said, okay, if we just have measurement distributions and no good method to get directly the state nor its entropy, we simply look at the entropy of the measurement distributions or the mutual information. For the entropy, we had to subtract the vacuum in order to observe something meaningful. For the mutual information, we simply take the normal definition and find a lot of things. In particular, for the scalar field, we looked at typical distributions generalized to the continuum, like distribution over field configurations, momentum field configurations, the Wigner distribution, and so on, and found precisely the area laws we know from the quantum entropies, in particular the area laws containing the central charge, C, something which tells you about the continuum. On the experimental side, we looked at the quench dynamics of a spin 1b C, where you can read out spin observables, more precisely sample from their joint Husimi distribution, and found that all these properties we have hoped for many, many years to see in quantum entropies can actually be accessed with the classical entropies we have proposed here. And on my personal wish list are many nice small projects which should show that classical entropies should solve most of their quantum analytics problems. This is just a few of them. One is to understand better how information flows in space-time, how it scrambles. If we can prove strict bounds on that, which so far we only have for 2-point correlators, stuff I do together with Martin. Then an important mention in this talk, the experimental perspective. We have now a very nice collaboration with Nottingham and Vienna, where we look at the setup of Jörg Schmidtmeyer. And I don't want to promise too much, but the preliminary results are really great. The curves fit extremely well. Then one could think about applying this to cosmological settings, also in analog scenarios, try to understand or make accessible the entropy of analog black holes, analog expounding spacetimes, and so on. Another topic I personally like is condensed matter style, in particular topological matter, because there you would like to understand the topological contribution to entanglement. You would like to know the central charge, because in many experiments, the phase of matter is changing through the experiment. And in general, understand better higher order correlations. How are they encoded in the mutual information? Investigate other systems, other degrees of freedom, spins, look at quantum phase transitions, many-body localization, and all these kind of things. Basically, try to play the whole game from simply a new perspective. I'm sorry to have spoken 5 minutes more than I was allowed to. I hope you liked it. Thanks a lot for your attention. And if you are interested, just drop me a mail.
Thank you, Tobi. That was perfectly fine. We are still well within our time. So thank you for a very nice talk. And because we still have some time, I would like to open this to a discussion. So if you have any questions to Tobi, please switch on your camera, unmute yourself, and start asking.
I have a question. Yeah, thanks for the talk. So, yeah, do you get any ultraviolet divergence in calculating these classical entropies? And yeah, if yes, how do you deal with them in the interacting series in particular? I'm interested.
Yes, excellent question. Sorry, let me just go back to the summary slide. I guess what you're referring to, if I understood you correctly, is that in this formula here, we have ln of L over epsilon. So the local divergence of entanglement entropies, you find exactly the same for the classical ones. So in this sense, we have to deal with the very same methods than we use for quantum entropies. I know two which are quite prominent. The first is abandon absolute entropies and look at relative entropies, or look at the entropy difference to the ground state. In both cases, the UV divergence goes away. Does this answer your question?
Yeah, thank you.
Okay, good.
Thank you, Sergey. Any other questions?
Yes, I mean, 1 second, I can also try to switch on my camera. And not working, sorry.
No worries.
Well, look, it was a very nice talk. I learned a lot by talking to you. And one thing I think you should mention, because there are some experimentalists here as well, is how many repetitions do you need for this distribution? So there is I would say one caveat, but this is always like that. There is no magic wand. So you need to have sufficient distribution numbers of repetitions or points in your distribution. Do you want to maybe comment a bit on this?
Thanks a lot for bringing it up. I want to apologize for not bringing it up, because this is, to be honest, the most important question. I mean, how many resources do you need? And there is no general answer, but for certain classes of distributions which are common in experiments, one can give very precise answers. In the simulations we have done here, the distributions become absurd after a few units of time. In particular, it's not even close to Gaussian anymore. So something like two separate exponentially falling off blobs. And in this case, we have used, you can see this on the plot here on the right, 10,000 samples, which for an ultra-cold atom experiment is already a lot. When the distributions instead remain close to Gaussian, and what I mean by close is have one blob and exponential tails, so something like exponential of minus x to the 4, so stuff you would expect in an interacting many-body experiment, then I believe that the region of 1,000 to 2,000 samples is sufficient.
It's still really cool. I mean, because it less, yeah, I mean, nothing is for free. You need to work for it.
No, unfortunately not.
Yeah, but this is a really, I think it is a fantastic way forward. And now it also, needs to be also analyzed how it compares to more conventional thing, looking at higher order correlation functions, but also has the advantage that it doesn't depend on, the initial state being Gaussian. So there is already a big advantage. I think it's just, you expect somewhere to be a little caveat. Otherwise, you feel like tricked that because it doesn't exist. So really nice.
Yeah, I didn't want to make the impression there is no caveat. I'm sorry. This is no. The number of samples is in the thousands regime for sure.
Yeah, but it's doable. I mean, 10,000, I think, is still an absolutely reasonable value. I mean, it's possible. I mean, there are people here. Eleanor, I think she has left, but they're experimentalists. I think you talk to them. 10,000 is within the doable, I guess.
Well, I think you can put like one condensate per 30 seconds or something like that. So that makes you what, 120 condensates per hour. 10,000, it's about 100 hours, ballpark, which is not that much if you think about the fact that that experiment can run continuously, right?
Actually, there's an interesting point because you say continuously, and I think I don't want to misquote Marcus, but when I was visiting Heidelberg and we talked about the experiments, he actually said they don't switch it off because stability is the issue, and switching on and off just causes problems. So it's, as far as I know, pity that Eleanor left, it's always running.
As far as I know, it broke recently, so I think now it's switched off.
No. No.
I hope they get it back together, but this is how it is, right? Yeah, these are delicate experiments, but when they're running, he doesn't switch them off, which is interesting.
Exactly. So I mean, it means that you just need probably a week of measurement time on one of the experiments, right? Which is not it's very realistic.
Yeah. Oh, this is super exciting. I think helium systems can run for a long time, right, Patrick?
Yes.
Yeah. So no, this is quite nice. It's very nice. Thank you, Tobi.
Thank you for these kind words.
Do we have some other questions? I think if not, and because we are past the 4 p.m. Mark, and also because Tobi is on a holiday today, I think we should thank him again for a very nice talk, and I'll be stopping the recording